Okay, my name's David Thompson. I'm here from Nicholas Hare Architects to talk about the St Paul's School Science Building in Barnes. Science Building was completed in January of this year, having started on site in September 2011. I'm going to talk a bit about the background of the project. It's got quite a long history. We were appointed back in 2006. I'll talk a bit about the aspirations for the new building and how the layout developed, giving a bit of a building overview. And then talking specifically then about the use of concrete in the building. It's used extensively both in the form of, externally in the form of this precast vaulted colonnade. And internally there's a lot of exposed concrete. There's very few applied finishes, and the concrete frame also contributes environmentally to the passive environmental strategy. Being a science building, there's a lot of services to integrate. The labs have drainage, gas, water supply. So the integration of services into the building was quite a challenge. And then just some concluding thoughts at the end. St Paul's School is a large independent school. It shares its site with its prep school, which is called Collett Court, and they both occupy this fantastic site on the south bank of the Thames, on the Barnes Peninsula. To the north is the A4, the Great West Road, and just to the right of the slide there is Hammersmith Bridge, which becomes Castleknock Road. The entrance to the school is to the south, the tree-lined avenue driveway, which meets a fork in the road, with the left fork going towards Collett Court and the right court heading into St Paul's School. Moving on then, the site has a number of constraints due to its situation. The school buildings occupy the centre of this boomerang-shaped site, and they're immediately bounded by a metropolitan open land boundary which prevents any building on the school's playing fields. So any sort of redevelopment of the site, the buildings would need to be concentrated on the footprint of the existing buildings, which necessitates a phased approach. Then immediate to the south, the school bounds onto the Castleknock conservation area, which is characterised by these late 19th century Victorian mansion houses. The site has got an interesting history, in that the school buildings that are there now were built towards the end of the 1960s out of a prefabricated system built called the CLASP system. And before that, the site was owned by Thames Water, and virtually across the whole site were reservoir filter beds, which were subsequently filled in and playing fields were built over them. But as a result of that, just underneath the surface, about 3 to 5 metres down, there are these old concrete reservoir beds, and the infill material that was used before the school was constructed was of quite poor quality. So NHA were appointed in 2006. Before that, the school had commissioned an outline master plan with a view to getting an outline planning permission defining the scale of any potential new development, the massing and the potential footprint. So back in 2003, this was developed by Patel Taylor. Some of the buildings you can see there in the sort of green colour are retained buildings, but the grey colour and the blue colour were zones for potential new development. So our development of the detailed master plan from our appointment basically respected the principles of the outline master plan, retaining the sports hall in the centre of the building, but then looking at how the new buildings could be introduced on the site with minimum disruption to the ongoing functioning of the school, and avoiding significant expense to decant teaching onto the playing fields. One of the principal aims of the master plan was an aim to reconnect the school with the river. It occupies this fantastic site on the Thames, but at the moment all the buildings, including the relatively newer ones on the site, really turn their back on the river edge. So our design for the Great Hall, for example, you can see on the left, incorporated very large north-facing windows which overlooked a new open riverside court with extensive views of the river. So then this slide represents the developed master plan. The buildings in the slightly lighter purple colour were developed in more detail. and virtually all the lighter purple buildings you can see there were developed and taken to detailed planning stage, which was granted at the end of 2009. The darker buildings there were for a future phase and basically were the remaining components of the master plan, and providing new general teaching for Collet Court and also the main general teaching building for St Paul's School. A new north-south axis was created by the colonnaded science building. So for a link from the main entrance and the south of the slide there, roughly in the centre, there was this new covered route and this north-south axis which connects the main entrance to the Riverside Court at the north. The master plan aims to create a grand new frontage for the school, of which the science building to the right of the elevation there frames the new main entrance. And the existing John Collet statue, who's one of the school's founders, would sit against this large stone backdrop. So this is what is on site at the moment. The science building is the L-shaped building which forms two sides of the new central courtyard. That's obviously now completed and being built. We're on site at the moment with the drama centre to the north of the plan there, and that's due to be handed over in August of next year. The small building to the left there is the substation, which ultimately in the master plan becomes part of the Great Hall building, but that was required to be built in advance as it was needed for the construction of the new buildings. So the school's aspiration then for the new buildings, they're really now suffering with the legacy of these 1960s class system buildings. The concrete looks quite drab now. They perform poorly thermally and acoustically, and the system is so lightweight that it's very difficult to adapt the building to modern environmental standards. And they're also suffer the common 60s legacy of being full of asbestos, which also makes renovation difficult. So the school wanted buildings that were going to be robust and last for hundreds of years, rather than the 40 or 50 years that their current buildings have lasted. The central courtyard, as we talked about, was currently a fairly drab, uninviting space. The sports hall presented a very blank elevation to one side of it. And the chapel building, which you wouldn't really know was a chapel when you look at it, had to be removed to make way for the new science building that was relocated elsewhere in the master plan. You can see the current main entrance to St Paul's School there, and obviously it was felt that this entrance wasn't appropriate for a school with such a grand history. Internally, the classrooms, the science classrooms and the science storage and prep rooms, they perform poorly in terms of daylight and ventilation. There's a distinct smell of ammonia in the science prep rooms, which highlighted the fact that the ventilation was fairly poor, and they did suffer a lot from overheating. So they really wanted their new science labs to be state-of-the-art and be robust physically and environmentally, so that they could go on teaching to the high standard that they held themselves up to. The existing science building also had no spaces in it for sort of open study and collaboration, or wireless IT spaces. So that was one of the key aims of the new building, to provide such spaces. So a brief look at the layout for the new building. As you can see, it forms two sides of the new courtyard. It was slightly truncated at the northern end to fit in with the school's budgetary constraints, but the intention is clearly that in the future the next phases of the master plan connect into the north end of the building, creating that north-south axis I mentioned before. So our ground floor occupies a number of different functions. It accommodates the new main entrance, to the right of which is the new reception and porter's lodge. Then plant occupies at the north. There's a science pupil entrance off the courtyard, a new careers centre, science storage and technicians, which links to the floors above via a lift, and then sixth form common room and reprographics and IT support on the ground floor. So that's just the view of that new main entrance and how it creates a new grand entrance to the school, which sort of announces itself from the approach. And the new colonnade creates a much more inviting and pleasant place to circulate in that central courtyard. So moving up to a typical first floor plan, the upper floors follow this same sort of principle. So there's 6 laboratories per department: physics on the first floor, biology on the second floor, chemistry on the top floor. And the north-south arm goes north-south with the circulation space against the existing sports building. And then the circulation flips so that on the south side of the courtyard, facing north, we created this open, informal study and display area, part of which the client was very keen. This advertised the work of the science departments to the rest of the school and provided an inspiring workspace for the students to work and collaborate. The prep spaces and the staff areas are at the sort of the heel of the L shape, where they need to be to both for supervision and also to service the laboratories from the prep room. So classroom spaces are clear and they work, they're daylit and they're bright, and they all the services that the school want to incorporate are incorporated in there. And that's just a view of that north-facing display and work area, which looks fantastic at night. These coloured recesses, the option is there for the school to inhabit them and display various things to do with the subjects and the research that they're doing. So then looking at a typical section, you can see at the ground floor there is the colonnade and the science entrance. And then above that, the three science departments are stacked one above the other, with this large circulation volume to the left. The existing sports building at this point comes up to about the second floor slab. So we really needed to bring a lot of light in, both from above and also from the elevation above the sports building, to give a lot of daylight into that circulation space, which you can see on the left. I've actually flipped that photo so that it mirrors the orientation of the section. So then looking at the external elevation of that courtyard, the precast colonnade sets a sort of a plinth at first floor level, onto which sits this very deep brickwork facade. The full load of that brickwork is supported off those precast lintels, and it's just the brick is simply tied back to the in situ frame. The elevation is built without movement joints. It's lime mortar, and expansion is dealt with at the end of the elevations. So then moving on to how concrete was used in the new building. The building has an in situ concrete structural frame, and at ground floor level, as I've already discussed, the precast colonnade is also partly structural. The columns are structural and carry the load of the in situ columns above, and the precast lintels carry the load of the brickwork. The reasons for choosing a concrete frame were addressing the school's desire for robustness. We wanted to use heavyweight materials that would last the lifetime of the building, potentially for hundreds of years. And there's also a simplicity and a clarity to working with an in situ frame, whereby on the left there you can see how the window openings were just built directly into the openings created by the concrete frame, with no need for any secondary framing or internal or external linings. And on the right there, that's a look at the north elevation where that open resource area is, and essentially there were no other finishes applied to those columns and that soffit. That actually, apart from the curtain walling on the elevation, that provided the enclosure. This also meant that by just glazing into the openings of the concrete frame, a weather type envelope could be created relatively quickly, and this allowed the brickwork frame, which required a lot of excellent workmanship from the brickwork subcontractor, to grow at its own pace and be built off the critical path. Concrete was also very appropriate for more sculptural areas of the elevation, such as the angled wall above the main entrance. The substructure to this was formed in concrete as a cantilevered thin wall tied into the slab of the terrace above, and this had to carry an enormous amount of weight, as the stone cladding to this wall was 100 mil thick, basically, so that the intention was that the school emblem could be carved into this, and may still yet be in the future. So as well as robustness physically, I mentioned that the in situ frame was also chosen for its environmental robustness, and that wherever possible the concrete frame was exposed in the building, including the soffits in the classrooms, but also the columns and shear walls in the circulation spaces were all exposed, sort of expressing the 4 metre rhythm set up by the colonnade at ground level. The labs are naturally ventilated with a single-sided strategy, which was tested with some CFD analysis by Arup at the design stage. And The analysis was actually proved to work without taking into account the thermal mass, but the thermal mass was seen as essential to give the strategy future robustness and help with things like potential future increase in IT use in the labs, which may increase the heat load of the building. So basically the building would have capacity to cope with future climate change and future changes of use. So the colonnade was formed in precast concrete. We needed a material that could give us a high quality finish which would complement the brickwork and the sandstone cladding. It needed to be a material that could be sculptural but also be constructed to a very high level of very tight tolerances to get the quality that we needed. So precast was a natural choice. It enabled us to create these sculptural vaulted forms, but also with things like the sills and copings to create details, as you can see in the bottom right there, where the sills are slightly splayed at the corners to throw water away from the joint. The section there illustrates a basic section through the colonnade, where the structural precast column sits on grid with the in situ columns above. And then you can see how the lintel, the thicker lintel unit, supports the brickwork on top of those columns, and then the vault units inboard of the lintel, you can see there with the insulation above it, that basically served as permanent formwork for the first floor slab, which was poured above. The process, we developed 3D drawings of each vault type and lintel type and column type at design stage. And we specified the type of finish that we wanted, a matte finish with a colour similar to Portland stone, and we were keen to expose some of the aggregate to create some visual interest. The design of these and the specification was developed with Techcrete, who supplied all of the precast concrete on the project. During the tendering process and the manufacturing process, we went up to their manufacturing facility in Brigg in the northeast, and you can see there some of the columns in construction. They came out of the circular moulds quite shiny actually, but when acid etched you can see that the micaceous aggregate was revealed, and there were various degrees of acid etching that we could go with, and we actually adopted the sort of standard acid etch. The deeper acid etch was a bit too rough to the touch. So then, looking more in detail at our visit there, the facility had basically a robotic rebar machine which basically bent the bars into the shape dictated by the drawings. These were then built into the rebar cages on site, as you can see in the bottom left there. And then the formwork were very carefully crafted, very skillful carpentry involved. And then the drawings above are the Techcrete subcontractor drawings, and just showing how that all comes together. The reinforcement had to consider the lifting loads and the stresses that the vault units would be under when they were actually lifted into place on site, and lifting sockets and bolts were actually cast in to the concrete at that stage. So then, how the colonnade was installed on site. The units arrived on a lorry and were then basically lifted into place on site. The precast was installed by Atlantic, the in situ frame subcontractor, and careful and accurate detailing was required right from the start, really, in that these columns, they were built with a 100mm hole in the centre, and that had to be lowered onto a 25mm diameter steel dowel, which was basically cast into the foundation. So those dowels had to be cast into the foundation accurately, so that the columns would be straight on and aligned all the way down the length of the colonnade. So once lowered into place, the central void in the column was filled with grout, and a similar dowel detail was adopted to tie the head of the column into the in situ structure above. At the bottom right there, you can see one of the lintel units. These were immensely heavy, and they were loaded into place by crane and placed on top of the columns. And then the next slide here kind of shows how this precast kit of parts was cast into the in situ frame, and the whole thing was unified whilst maintaining a thermal break to the internal in situ frame. So the image on the right is looking down on top of the the lintel unit, and you can see the 25mm diameter dowel coming out of the column. And that zone in there was then infilled with an in situ concrete stitch, if you like, which tied those components together. On top of that was placed a thermal brake pad, and then insulation, and then the in situ column was formed on top of that, tied together by the 25mm dowel that goes down into the pocket in the in situ column. So once in place, then the bolts were supplied to site with these steel hangers, which you can see there, and these were used basically to tie the bolts into the in situ slab when it was poured above. So extensive false work and temporary support was required for these bolts so that they could act as permanent formwork for the slab above. Insulation was used to basically fill the void between the precast units and the in situ slab above to reduce weight, and also obviously to provide thermal insulation. So the image on the bottom left there shows a typical situation where you had the precast colonnade on the left and then the in situ slab on the right, which formed the internal in situ soffits to the ground floor. And that's what you're left with at the end of that process, the in situ concrete frame on the left and the colonnade on the right. And this meant that all the external finishes, the stonework, the curtain walling, basically had to be built up to that precast vault construction, which required very careful execution on site and was very successful. So internally, as I've spoken about the in situ concrete frame, the structure was a simple flat slab and downstand beam structure with extensive amounts of exposed concrete soffits. We also had internal exposed circular columns, large areas of visual wall concrete, and also the main stair flights on the north-south elevation circulation route were also cast in situ. The mix that we used was subject to quite a lot of development on site, because initially the sample panels that were built were suffering quite a lot from large blowholes towards the top of the formwork. We'd specified initially a mix that included 50-60% GGBS in the mix. We wanted a light creamy concrete, but the curing time involved in that high percentage of GGBS didn't fit with Macy's program, and a compromise was reached where the final mix was about 35% GGBS with some limestone, crushed limestone in the mix to create the lighter colour. There was a lot of experimentation done between the mix of standard and self-compacting concrete to try and reduce these blowholes and also the size of aggregate. And after about 9 attempts, Atlantic got to the mix that we needed on site, and progressed from that stage onwards. It was useful that we had the ground floor area where much of the area was given over to plant and storage, where we could experiment with the finish and establish a benchmark of quality that we could be rolled out across the upper floors of the building. So then the formwork, we developed detailed formwork setting out drawings for each level of the building. It was a Visaform product was used for the formwork, paper faced to create a matte finish, and the joints and the level and the quality had to be very closely monitored on site, and was executed very well by Atlantic. The same form as that the precasts that Techrete used for the circular columns was used for the in situ columns, which are a repeater-backed circular former which creates these columns with no seams, and they were also very successful. So the quality of the internal concrete came out very well. That's an image there of the open resource area, and the classroom soffits create this nice creamy colour, and you can see the daylight is very good in the labs despite the use of concrete, and we managed to avoid large areas of ceiling and false bulkheads, which was desirable. Then internally, that's a view of the main circulation space. You can see there's the shear wall on the right, achieved a good finish on those vertical surfaces. We worked very hard with Atlantic to coordinate bolt hole positions in the formwork. And then also the main staircase on the left as they were constructed in situ and they had to span a very large distance, there was 9-meter flights. The waist on the stairs was very deep. They were about 350 mil deep. So to try and reduce the visual impact of that, we did that with our balustrade detail, which cloaked part of the side of the tread, but also the underside of the flights had this chamfer detail, which worked nicely and was executed very well. It did require very careful carpentry on site, and the next slide shows how this was executed. The main circulation space on the left there shows how this in situ flight links all 3 levels of the building, and the top surface of the staircase is left exposed. That is the finish, and a rebate was cast in for the nosing, and those again were executed very well on site. I mentioned earlier the challenge presented by the integration of services into this building. It's a science building. The labs have all the services that you would expect in a state-of-the-art school science lab: gas, drainage, water, power. So all these services had to be integrated into this structure within this aspiration. No ceilings, no raised floors. The zones we had to play with were the plinth zone of the fixed perimeter benching, some risers in the corners of the labs, and a high-level acoustic bulkhead at the perimeter, which, together with the lighting rafts, met the acoustic requirements of the classroom. So at design stage, to test that this was going to work 3-dimensionally, Arup developed a 3D services model, which you can see there on the right, which confirmed that the zones we had were workable. And this had to be then taken on by the M&E subcontractor on site and developed into full installation drawings. Similarly, the power and containment, there was no raised floors in the labs, so the power and for BMS and for sort of plug-in sockets for the central tables, also the AV and power connections from the island teacher's bench to the interactive whiteboards, all had to be cast into the slab and coordinated in advance of the slab pour, so that risers and pockets for floor boxes and things could be set in exactly the right position. So there were 2 challenges in this: basically getting everything coordinated in time and allowing for potential future expansion by the school, but also meeting all their requirements at this relatively early stage in the program, and also making sure that these casting services stayed in place when the concrete was poured. So that also required very careful control on site. So the image at the top there, you can see all the containment as it sat within the rebar, and then after the pours, these plywood breakout boxes were broken out, allowing for the installation. And then, as a conclusion, this slide kind of sums up the project well, in that it shows on the left the precast vaults of the colonnade coming internally and forming the finished surface in the science entrance area. And you can see the services, the lighting services, the smoke detectors and everything were cast in, which meant that at a very early stage, the whole team had to coordinate and work out the requirements and work out exactly how that was going to be done, bearing in mind there's an insulation and an in situ slab poured above. And so that those units could be made on site in the northeast with the holes in exactly the right place. And that was achieved very well, and I think the team, I mean, May should take credit for this, in that they were involved in the project from an early stage, because initially the project was procured via a management contract, and Mace were management contractors. So we had they were part of the design team essentially up till stage F. And we worked through a lot of the detail with them and their subcontractors. But then at that stage, the school decided to adopt a different approach and switch to a single stage design and build contract, which Mace was successful in securing, and then ourselves and the rest of the design team were novated to Mace. But the spirit and the relationships we developed with the main contractor kind of continued despite the change in procurement route. So despite it being design and build contract, the spirit of collaboration that we'd developed through that management contract process was carried through, and I think that really was instrumental to the quality of the final building and its successful delivery.